Welcome back to The Explainer, everyone. I'm absolutely thrilled you're here today because, wow, we are going to unpack one of the most intense, highly engineered, and honestly downright dangerous processes on the entire planet. So let's just dive right in. We're tracking the epic journey of a single uranium atom. We're going from a seemingly ordinary rock buried deep underground all the way to the glowing core of a nuclear reactor. It's a huge testament to human intellect, and I promise you, by the end of this, you're never going to look at a light switch the exact same way again. Now, to really understand why we go through all this insane trouble, just imagine a tiny pellet of uranium, something roughly the size of a peanut. If you wanted to match the energy packed into that one single microscopic pellet, you'd actually need to burn an entire ton of coal. It's absolutely mind-blowing, right? We're talking microscopic scale versus massive energy output. And to push that scale even further, that exact same peanut-sized pellet is also equivalent to burning about 564 liters of oil. But, as you probably guessed, unlocking this immense hidden power isn't as simple as just lighting a match. It requires navigating what's arguably the world's most complex and perilous engineering gauntlet. Section 1. A brief history of uranium. To really grasp the stakes here, we've got to jump back in time a bit.
For centuries, uranium was just kind of sitting there, treated like any other ordinary, unremarkable metal. Nobody had the slightest clue about the universe of energy hiding inside. And what's really interesting about this timeline is how slowly the pieces actually came together. Klaproth discovered the element way back in 1789, but it wasn't until 1896 that Becquerel noticed something super weird. Uranium was emitting radiation entirely on its own, no outside trigger needed. Then, fast forward to 1932, Chadwick discovers the neutron. But the absolute game changer came in 1938 when Hahn and Strassmann fired neutrons at uranium atoms and actually watched them shatter. They achieved nuclear fission, unleashing just a staggering amount of energy. Boom, the atomic age was officially born.
But we immediately ran into a massive engineering problem. Natural uranium, straight out of the dirt, is practically useless for generating power. Why? Because a massive 99.3% of it is an isotope called U-238, while a minuscule fraction, just 0.7%, is U-235.
So, understanding the difference between these two is absolutely crucial. U-238 is mostly stable and inactive. It really just kind of sits there doing nothing. But that incredibly rare U-235, that is our golden ticket. It's highly unstable, and it readily provides the energy we need for nuclear fission. So to get any usable power at all, we have to figure out how to isolate and boost that tiny 0.7% of U-235.
Now, boosting that U-235 is what we call enrichment, and history shows us the crazy dual nature of this exact same element. During the Manhattan Project in World War II, scientists enriched uranium to over 80%, which gave us the destructive force of the atomic bomb dropped on Hiroshima. But today, for peaceful civilian power plants, scientists only enrich the uranium to about 3 to 5%. So it's the exact same element, just an entirely different engineering goal. One is for controlled electricity, and the other is for sheer destruction. Moving on to Section 2, mining the dangerous rock.
So how do we actually get this stuff out of the earth? Well, we're looking for a mineral called uranite. And in places like the incredible Cigar Lake in Canada, engineers have found these extremely high-grade deposits where the uranium purity is well over 20%. But nature doesn't exactly just give it up easily. At Cigar Lake, this highly pure ore is trapped directly beneath heavily waterlogged sandstone. If miners simply started digging, water would instantaneously flood the tunnels. It would be an absolute catastrophe. So how on earth do you mine a flooded, highly radioactive rock?
Honestly, the solution they came up with is absolute genius. They use a technique called artificial ground freezing. First, engineers drill hundreds of deep pipes straight into the earth, and then they pump in calcium chloride that's chilled to minus 30 degrees Celsius. This literally freezes the groundwater in place, creating an impenetrable wall of solid ice. Once that ice wall is locked in and secure, they use remote-controlled machinery to actually carve out the rock. This means no humans ever enter the immediate extraction zone, which perfectly protects the workers from both cave-ins and severe radiation.
That brings us to Section 3, the complex enrichment process. Okay, let's step out of the frozen mine and into the chemical plant. The rock is out of the ground, but remember, it's still mostly the wrong type of uranium. So it's about to face its most extreme trials yet. First, the raw rock is violently crushed into a fine powder and mixed with water to form this wet slurry.
Then it gets blasted with insanely strong acids that dissolve only the uranium, leaving all the impurities behind. But here is the absolute wildest part. To enrich it, engineers actually convert this solid material into uranium hexafluoride gas. And let me tell you, this gas is extraordinarily hazardous. It requires meticulous, pinpoint handling by the engineers. And this brings us right to the most critical turning point in our explainer: uranium enrichment. That dangerous gas is pumped into ultra-fast centrifuge machines. These incredible machines are designed specifically to exploit the minuscule weight difference between the heavy U-238 and our lighter, super valuable U-235. The physics inside one of these centrifuges, which, by the way, are spinning thousands and thousands of times per minute, is absolutely fascinating. The intense centrifugal force violently pushes the heavier U-238 molecules right to the outer edge of the cylinder. Meanwhile, the lighter, prized U-235 gas gathers perfectly in the center. So they extract that center gas and run it through the spin cycle again and again and again until it reaches that exact perfect 3 to 5% energy grade required for a power plant.
All right, Section 4, inside the nuclear reactor.
We are finally reaching the climax of our atom's journey. We've got the right grade of uranium, but we obviously can't just toss a highly dangerous gas into a reactor. It needs to be transformed back into solid fuel. So the gas is chemically converted into uranium dioxide powder. Then that powder is pressed into those tiny, peanut-sized pellets we talked about at the very beginning. To make them incredibly tough, they're baked in massive furnaces for 24 hours straight. Finally, robotic arms seal thousands of these little pellets inside special tubes made of zirconium. And zirconium is amazing here because it easily withstands extreme heat and corrosion, but crucially, it allows neutrons to pass right through it without any interference at all. And this is where the magic happens. Inside the reactor core, neutrons collide with our highly engineered U-235 atoms. The atoms violently split apart. That's nuclear fission. This split releases an immense amount of heat alongside brand new neutrons, which then go on to split more atoms in this massive, continuous chain reaction. And what do we do with all that intense heat? It's simply used to boil water, creating high-pressure steam that turns massive turbines, which ultimately sends electricity directly into your home. Pretty wild, right?
But the story doesn't end when the electricity is generated. Let's look at Section 5, handling the radioactive waste.
After about a year inside the reactor core, our atomic protagonist is pretty much exhausted, and we enter the final, very sobering chapter of its life cycle. These spent fuel rods cannot just be thrown out in the trash. They remain incredibly hot and dangerously radioactive. Handling them requires an entirely new, deeply serious set of engineering protocols just to protect humans and the environment.
To safely cool down and contain all that dangerous radiation, these spent rods are carefully submerged into massive pools of water that are like 25 to 30 feet deep. And they don't just sit there for a couple of days. They have to remain submerged in these cooling pools for a staggering minimum of 10 years, just cooling down. Today, there are literally millions of these spent rods stored exactly this way all around the world. Which brings us to our final thought. The journey from a flooded rock in Canada to a glowing pellet powering vast cities is just astonishing. It's not just chemistry. As the quote says, "The journey of uranium is a profound testament to human intellect and our courage to tame nature's most dangerous elements." So, the next time you effortlessly flip on a light switch, I really want you to remember the invisible, highly engineered, and deeply dangerous journey that makes that simple little spark possible. Thanks so much for joining me for this explainer, and I'll catch you guys next time.